Hello everyone and welcome back. Last time we talked about the linear hypothesis and we proceeded to optimize it with linear regression using a square loss that looks something like that. But why a square loss, not an absolute loss? This will be the question that we will answer in this video. Well, the first thing to realize is that we're assuming some kind of noise distribution around the mean. So what we'll cover here is a probabilistic interpretation of ordinary least squares and how you can get the square loss simply out of this assumption. The assumption that the outputs are simply some linear model plus a Gaussian noise. Epsilon is a random number that is sampled from a Gaussian distribution. So imagine yourself walking along this line, which is the hypothesis you're looking for, and the points will be distributed in a Gaussian manner around you, so left and right. So what this means is that we have this kind of Gaussian distribution, you're at 0, and then the noise is left and right with exponentially decaying probability. And this is a continuous distribution, so if you really want to know what's the probability of the points being in a certain range, sigma, where sigma is the standard deviation, to 2 sigma, then you have to integrate that normal distribution. And this means it's a normal distribution with mean 0 and variance sigma squared. So if we start with that assumption, simply the assumption that we have some linear model and we're adding Gaussian noise to it, can we derive the loss function? This will be the task. So first of all, we can write the assumption like that, where we say that the probability distribution of epsilon, I, for a given example, I, is simply this Gaussian, where now epsilon shows up here. Right? This is exactly a description of this distribution. And we can replace epsilon, since we have, x and y are different. We're given x, and we're trying to predict y, then the question becomes, what's the probability of seeing the output y given x? So we can translate this like that, where we have probability of y given x. Now it's a conditional probability. We still don't know what theta is. Theta is a fitting parameter, and it can be expressed like that. All we did here is we replaced the value of epsilon in the equation, so we get this expression. So it's a conditional probability of y given x, and then we just replace it and we have an expression for it. So what can we do with that? We can now define something called the likelihood. The probability of seeing an example yi given an input xi now is a Gaussian. We know the form of that equation, but we want the probability over all the data set. So if you remember from probability, if we have the probability of event A and B happening, of seeing example I and I plus 1 and I plus 2, all these different examples, 1, 2, 3, let's say, usually you get a joint probability. So that's probability of A and B and C. And since we're assuming that they're independent, you're sampling these examples independently, now we can express it as a product. So it's a product of probabilities. And this assumption is called the independent and identically distributed assumption. Otherwise, we cannot write it that way. So once we have that, this is a likelihood over all the data set. Now it's independent of which example we're looking at. We're looking at all examples. Then we can just replace the expression we had before in this equation, and we have a product over all n examples of this Gaussian distribution. Now, the purpose is, this is the likelihood of seeing an output given the input. So the purpose would be here to maximize the likelihood, maximize the probability to see y given x, and given theta, we've assumed also a structure for the model. It's theta transpose x. It's a linear model. We've made an assumption of what the model looks like. And we're maximizing, of course, subject to theta. Theta is the optimization parameter we can actually control. But maximizing a product of exponentials is really hard. So that's why we want to define something called a log likelihood. If we log this function, the optimal theta will stay the same. But it will be a much easier function to deal with. So we take this likelihood, we log it, and we get the log likelihood. So now log of the product of these exponentials, what does it look like? And you can already maybe see the convenience. There are 2 benefits in this case. So try to do it by hand and see what is the log of the product of a bunch of functions. Pause and think. So that's simply the sum of the logs, right? So it's the sum of the logs of the exponentials, and you can see that there's a log and an exponential that can cancel out. So all you need to do here is the log of a product is the sum of logs again, and you end up with this expression. N log, so this is a constant as a function of theta. This will not change as we change theta, so we can just completely discard it. And now we have the negative of the sum of squares. So hopefully you can see where this is going. So if we want to maximize the log likelihood, then all we need to do is maximize this expression, which means maximize this expression, and therefore maximizing half or minimizing half of the sum of yi, the prediction, minus, the true label yi minus the prediction theta transpose x squared. So this is the justification of where the square loss comes from, what it assumes implicitly. So when you're using a square loss, you're implicitly assuming that the noise around the signal, around the linear hypothesis, is Gaussian. So what if the noise is not Gaussian? What happens if the noise is a Poisson distribution? Can you still come up with a loss function based on the distribution? There's a whole set of models that are called generalized linear models that start from the distribution and derive the appropriate loss for it. So we'll talk about that next time. Thank you.